Good morning, everybody. My name is Gary Bolton from the National Nuclear Laboratory, and we're hosting today's webinar from our Warrington offices. Just a couple of sort of housekeeping matters before we start. The webinar is being recorded, and it is an open forum, so there is an opportunity for questions at the end, and I would just ask you all to sort of respect the presenters who in some instances may not be able to answer all questions. People are joining the webinar by computer and by phone. If you're on a phone line, could I ask you to mute your phone line and obviously unmute it if you need to ask a question at the end. Questions can be submitted via the BlueJeans software for those of you connected in via that means. And I can read out questions at the end. Rick Short is unable to join us today, so I'm just going to go through Rick's introductory presentation before handing over to our technical lead today, who's David Wickenden. So the structure of the webinar today, I'll do a brief introduction to the Bursary call, which should take about 5 minutes. As I said, I'll then pass over to today's technical lead to go into more detail on this characterization theme of the NDA PhD Bursary call. And then we have some time at the end for questions and answers. So why does the NDA support university research? One of the main reasons is maintenance and development of key skills to undertake the NDA's mission over the coming decades. So this is to keep industry supplied with the correct skills, but it's also to ensure that there's academic capability to train the next generation of students and ensure that they have the necessary skills to help with decommissioning. Many of the research projects that NDA fund help to provide fundamental understanding of technologies and processes across the NDA estate. Much of the work supporting PhDs is at the lower end of the TRL scale. However, these projects feed into the more innovative programs supported by NDA. A key element of the program is knowledge transfer. All PhD projects have an industrial supervisor to help steer the research towards industry's needs, but also the supervisor takes the learning from the project, ensure that this learning, this knowledge gets back into industry. This slide should help with preparing your bursary application and shows a difference between the type of research funded by the Nuclear Decommissioning Authority and that funded by the site license companies. So areas of interest to the NDA are maintenance of key skills, as I've already touched on. They're looking for PhD applications that are innovative, and also looking at research programs that help them to support strategic decisions. As opposed to this, research funded by the site license companies is much more about improving the baseline for that particular site's cleanup. So this R&D is much more site or plant specific, and it's often needs driven, or it may be to maintain a specific capability on that particular site. And this final slide just includes some figures demonstrating the lengthy timescales and the high cost of achieving the NDA's mission. And really the ultimate aim of the research sponsored by NDA is to reduce these numbers, both the timescales and the cost. So the program is currently estimated to last over 100 years and will cost in excess of £100 billion. So if we can make even a small percentage difference to this overall cost, that has a significant saving, and all of this money is, of course, taxpayers' money, which could be spent on things other than nuclear decommissioning and cleanup. So that's a short introduction to the scheme, and I'll now pass over to the technical lead today, David Wickenden.
Technical lead. Well, I don't know about the technical bit, but I'll endeavour to take you through what the Characterisation Working Group is and what we're trying to achieve. The Characterisation Working Group covers the practitioner community within the site licence company estate and other nuclear clients such as EDF and Ordermaster. Now, our concern, as it says on the slide, is to promote good practice in all aspects of the characterisation process and encourage a culture of continuous improvement. That means we look for gaps. We look for gaps in things. Where can we improve things? Can things be done better? Does new technology need to be developed, or new techniques need to be developed to meet emergent issues? And when we identify these gaps or these themes, we then communicate them to the committee, Nuclear Waste Decommissioning Research Forum, who then use that to inform the R&D strategy of NDA through the NDA Research Board. Next slide, please. Now, currently, of course, we do have the techniques in the vast majority of cases, and we are able to do the job. But that's not to say there isn't room for improvement in order to do things more effectively, more quickly, and, dare I say it, more cheaply. Oh, where's that coming from? Do we have a cross line?
Perhaps if you're on a phone, you could mute your line, please. Thank you.
Is that muted? Can you?
Thanks so much. So, and dare I say it, cheaper. So, our two main themes are as stated on the slide. We're looking for improved in situ analysis, improved instrumental techniques for plant structures, land, for radiological and chemical contamination. We're looking at remote field sensing technology, methodology, analytical for contaminated land, buildings and waste packages, and or indeed improved detector design for surface and remote monitoring. The other side of the coin, of course, is the laboratory, because of in situ field measurements will help inform on the management of structures, surveillance to identify areas of concern, and or to provide triage for taking samples from large demolition jobs and to inform clearance exemption. But at some point, samples need to be taken and they need to be sent to the lab. And that is an expensive option. The value of it is without question worth the cost, but nonetheless, we need to strive to ensure that that analysis is done as effectively as possible. So we're looking, and also we have challenging timescales. So we need to better match the time it takes to perform analysis with project delivery. So we're looking for more rapid analysis methodology, principally to support perhaps automation in sort of labour-intensive areas such as sample prep and separation. And with the aim of improving analysis cost, its turnaround, and improving through automation the supply chain capacity. This is of particular note of concern at the moment because Magnox, for example, is entering a stage in its life cycle which is heavily dependent on upfront characterization. So the cost and turnaround and speed is something that's of concern. Now, with regard to the types of radionuclides, the key focus is on alpha and beta radionuclides. Think soft betas such as tritium, carbon-14, hard betas such as chlorine-36, the usual strontium-90, etc. And the alphas, of course, the actinides, but also including norm nuclides such as radium-226, lead-210. etc. Next slide. So let's follow this through with a few illustrations. In situ analysis. Now, in the top right corner, you have a picture of the Bradwell turbine hull merrily being taken apart. Of course, the waste from that needs surveillance against the established waste stream fingerprint to ensure that the route of clearance exemption is appropriate. Then, at the opposite end of the scale, picture in the lower left-hand corner is a historical picture of the installation of the Windthrift pipeline. There you can see two buried coaxial pipelines being constructed. In this particular case, it's a seamless pipe running for several miles across land and then out to sea. It'd be interesting to know what's inside it with regards to surface scale for the purposes of informing its removal or perhaps even in situ disposal. Whatever the case, we need techniques for characterizing, identifying the radioactive burden within it. And there are many other examples of inaccessible or hazardous environments where it's not convenient to send people in. So we're talking about remote building, plant contaminated land surveillance, remote sampling techniques for hazardous environments, improved and all new techniques for in situ analysis of waste. We've supported this work, and there are two examples here. In 2015, we funded development of long-range scanning-based detection of alpha-induced efflorescence, which is in progress with the University of Lancaster. And in 2012, we supported the development of rapid and accurate assessment of radiologically contaminated rubble, which was performed by Imperial College London. Next slide. Similarly, more recently, in 2016, we supported the development of novel test stick extracted technology. Basically, these are sticks or plastic surfaces on which a extractant is coated, which then fluoresces. And so they're looking at direct contact extraction and then reading the plates on a phosphorus screen plate reader. This offers the opportunity for very rapid in-field measurements. Similarly, in 2015, we also supported, again with the University of Lancaster, in situ real-time monitoring of waterborne low-energy beaters. This is more from the perspective of land contamination management. Next slide, please. Similarly, in 2012, I do like this because it's innovative, because it's using biosensors to look at the levels of uranium, etc., in aquifers or groundwater. Very nice piece of work, but this is an example where we're not looking for technology transfer so much, but we are looking for true innovation, something that's a little different, because only then will we start to see step change in the technology and methodologies. Next slide, please. So here's one for you, out of the box, swarm robotics. People are looking very much at software development for small, inexpensive robots to conduct search and rescue in earthquakes, to conduct chemical surveillance in a contamination scenario. Could this kind of technology be developed for the RAD environment? I'm thinking here perhaps inaccessible vaults. Sending people sending these robots in, should there be an incident where it's too hazardous to send people in initially to perform the survey. It's a bit agents of S.H.I.E.L.D., I admit, but this is the sort of thing we're looking for. We're looking for innovative approaches. We're looking for other areas in the academic industry for ideas, for concepts, for technology that can be transferred in an innovative way, in a novel way, into the nuclear field. And one of the issues we do have, as I mentioned previously, is the ability to go into inaccessible hazardous environments. Next slide, please. Now we come on to the other side of the coin, as I said previously, which is rapid and automated analytical techniques. Now, we've been doing a lot of work on this over the past few years, and the following are just a few examples of that. In 2016, we supported a bursary with the University of Cardiff to develop smart media for fast, low-cost radionuclide analysis. Basically, this was building on earlier work to design and synthesize novel extractants for specifically targeted liquid scintillation counting or fluorescent counting. These surfactants are now looking at putting these onto a matrix, so as to form a smart media card, if you like, which will then selectively extract from whatever medium you might be looking at. So this is another example of a very sophisticated technology being developed in conjunction with material scientists, organic chemists, and the like. Next slide, please. Another example here is with the University of Southampton, who are looking at automating analytical techniques. And this 2012 bursary is coming to completion, and recently was figured in a Royal Society of Chemistry Radiochemistry Group seminar at Southampton, which was looking at the development of these techniques across the world. We had some very interesting presentations from Kerry, for example, in Korea, on the work they've been doing in conjunction with the Japanese Fukushima. So these are kind of things that we would like to encourage. So it's not just the technology, but it's also the extractants used to achieve the separation of various radionuclide classes. So applications to a wide variety of different radionuclides and the like. So that, in a nutshell, is what we're looking for. Improved in situ techniques and rapid and automated analytical techniques to support the need to be able to analyze our wastes, to survey our nuclear environments, whether that's land, plant, or structure, as effectively or more effectively, more rapidly than perhaps we can do at the moment. And I thank you for your time. I'll try and answer any questions you may have, but if not, I'm sure Lindsay can take a note of them and pass them on to me after this meeting, and I'll endeavour to reply to you by email. Thank you for your time.
Okay, thank you very much, David. So we can have questions either over the phone line or typed in via the BlueJeans software. If anybody wants to start things off, we'll give it a few minutes, and if nothing's come in, then we'll close down today's proceedings. Okay, it looks as if there's no questions for David today, so I'd just like to thank you all for joining us today. Hope you found it useful. If you're thinking of applying for an NDA PhD bursary, the deadline is the 21st of October, so please bear that in mind. We've just had a question in saying, thank you for the presentation. I would like to know if there is a restriction on who can apply. My understanding is that the call is open to all universities in the UK, so from that aspect, there's no restriction. I hope that answers the question. Great, okay. So, do we have a message? No, that's just, sorry. Okay, so it looks as if there's no other questions. So yeah, once again, thank you for dialing in. Thank you to David for his presentation. And we look forward to receiving your applications if you decide to submit one. Thank you.